far in this lecture, we have talked about different techniques of evaluating numerical integration. We have talked about trapezoidal rule, Simpson's 1/3 and 3/8 rule. We have discussed few examples on trapezoidal and Simpson rules. Then we talked about Gaussian quadrature. We will now come to double integral, and specifically we want to point out that double integral requires use of these techniques. It's not a new tool, it's just repetitive use of these techniques will help us to evaluate double, triple or any higher integrals. So let us see how we do it. Let us go back to our problem of evaluating area of a circle. Here we have an unit circle, that is r equals 1. The center of the circle is at the origin, that is 0.00, and we have discussed that area of this circle is 4 times 0 to 1 y dx, and y in this case is 1 minus x square, since this circle is x square plus y square equals 1. When we write y dx, this y dx is actually this small area here, strip of area over this dx and y. Since this is small, this is treated as a rectangle, therefore the area is y dx, and then we span this idea from x equals 0 to x equals 1. Another way of looking at this problem is using double integral. That means integral over the area over dy dx. In this case, the area dy dx is a small rectangle here, and then we span this small rectangle over the entire space. So it can be written as x goes to 0 and 1, y goes to 0, root over 1 minus x square. What does that mean is that we are evaluating this part. In this part, this small area I am spanning in this y direction. I am calculating area over here, and then I am going in x direction, then I am taking it in this direction. So as I go in y direction, I actually get this kind of an area, and you remember that this area we are taking in x direction, so we are then taking in x direction. So here we sweep in y direction first, I get the area in y direction, and then I sweep in x direction. Another way is, of course, I sweep it in x direction first. That means I get an area like this first, and then I go in y direction. Then the order of integration will be different. However, here, even though I am sweeping in x direction first and then y direction, the results from both of this expression must be same. Otherwise, we will have a problem because both of them indicate the area of the circle. It should not matter that in which way I do the integration. Now, how do we actually evaluate this integral analytically? When we analytically evaluate this integral, what we do here, this part we complete it first within the third bracket. This part we complete it first, and when we do this integration, we completely forget about what is there outside it. So as I do this integration is y within limit 1 minus x square and 0. So this integration will be root over 1 minus x square. So it comes x equals 0 to 1 for root over 1 minus x square dx. We have to evaluate this integral. So this is the first step. Second step is evaluating this. And analytically, we know how to evaluate it. So it's basically we replace x with sine theta, and then it is 1 minus sine square theta. And then we can write dx equals cos theta d theta. X equals 0 gives theta equals 0, and x equals 1 gives theta equals pi by 2. So limit I have changed 0 to pi by 2, 1 minus sine square theta cos theta. And it gives us 4, 0 to pi by 2 cos square theta. 1 minus sine square theta is cos square theta, and 1 cos theta here. Then this cos square theta, I replace it by 1 plus cos 2 theta, which is equal to 2 cos square theta. So this becomes 2. Now we can perform the integration, and it will come down as 2 theta sine 2 theta by 2 here. But that really doesn't matter. Within 0 to pi by 2 limit, this becomes 0. Only this theta remains. Therefore, it gives us the value pi, which is indeed the area of this unit circle. Now see that we are getting pi. We are not really getting the value of pi, which we were getting when we numerically evaluated the integral. So in certain cases, as you see, that even though analytical solutions are available, numerical solutions we still perform to have more information. Anyway, so overall procedure in analytical method for double integral is what we have just seen. We have two single integrals we have evaluated. That's it. But numerically, this is slightly different. So let us see the example taking trapezoidal method. So in trapezoidal method, the rule is I equals h by 2, y0 plus 2y1, 2y2, etc., etc. If I want to use this to evaluate this integral, what I'll do, I'll treat this as my y, and I'll evaluate this y at different location. This y0, y1, y2, etc. are value of y at different x location, which means each of these y0, y1, y2, etc. are actually this integral, value of this integral for different x. What kind of value? So for instance, y0, we start from x equals 0. This integral y0 to root over 1 minus x square for x equals 0. This is one particular x. Similarly, y1, y equals 0, 1 minus x square for x equal to 0 plus h, so on and so forth. This is how each of this, when we evaluate, we have to evaluate this integral. This is once again numerically we have to evaluate integral. So all of this y0 to yn, we are getting by numerically evaluating the integral. So it requires a series of integrations. So numerical double integral is essentially a series of single integral, as opposed to the analytical double integral, which is basically two single integrals. Here there are a lot of single integrals. So overall the process is way more complicated now. So we would like to see that how this process can be implemented in a computer. But since this process is pretty complicated, we'll do in a slightly different way. So let us say we wish to find out the area of the circle, or to be specific, the value of pi we wish to find out using the double integral. I'll directly use this SciPy routine. This is a Python package, scientific Python. So this scientific Python package I'll use, and I'll evaluate this 4 times this area. This is the area of quarter circle, and 4 times this quarter circle area will be the value of pi. So here in SciPy integrate, there is this dBl quad. This gives a double integral using Gaussian quadrature. So first we have to define the function that we are going to integrate, and that is the integrand. And integrand in this case, that is simply 1, because I have only 1 here, I have nothing else. So integrate in 1, then x lower limit is 0, x upper limit is 1, 0 to 1, then y lower limit could be a function of x, that is why lambda x, but in this case it is 0. Y upper limit is also, it could be a function of x. So this is root over 1 minus x square. This mt is the math. So the square root, to evaluate square root, we are using this math package. So this is the lower limit of y, upper limit of y is root over 1 minus x square. So now we are ready. We can actually calculate this integral simply from SciPy. Within SciPy, I have to give the input of this integrand. Integrand means this function here. Then lower limit of x, upper limit of x, lower limit of y, and upper limit of y. And it will calculate two quantities. One is the result of that integral, another is the error. So this routine uses Gaussian quadrature. In fact, it uses 10-point Gaussian quadrature. And so it's a very, very high accuracy result. And then it even compares the result with a higher order quadrature. And between these two quadrature, what is the difference? That it calculates as error. So this error is not the difference with analytical solution, because you cannot have analytical solution for all kinds of function. Error is between two different evaluation of integral. The basic is this 10-point Gaussian quadrature, and then there is even a more accurate estimation, and between these two they calculate the error, which is usually very, very small. If I run this case, the output comes as 3.14159, etc., etc. So this is a very accurate value of pi. You can see it. So this Gaussian quadrature, it has given us highly accurate value. We can take one more example, that is the calculating the centroid of this quarter circle using the same routine. So in this case, we have to understand that how we can calculate the centroid. So the theory suggests that if we have this centroid coordinate xc, yc, recall that we are taking the centroid for this quarter circle here. This is 1, x equals 1. So xc will be x dA, integral of that, divided by dA. This is the theory, and I really don't want to go to the theory. This is moment of area divided by area. You can open up any physics or mechanics book to get the theory. But this is xc. Therefore, here I put this x. So my integrand is now x. And this dA, integration dA is of course a, and that is pi by 4. So here this is pi by 4. This integration divided by pi by 4. Why xc and yc are equal? Well, because of symmetry. If I have xc here, there is no reason why yc will be somewhere else. So because of symmetry, we understand it will be here. This problem is a standard problem in mechanics as well as in geometry. You can evaluate this integral analytically, and you will find that this xc will be 4r by 3 pi, where this r is the radius of the circle. So here, if I run this case, so please see that there is no difference between the previous case and this case. Everything else is same. Only thing I have changed here is that here the integrand has changed to x, and the result means this integral divided by pi by 4. So 4 divided by pi. This mt.pi is math.pi because pi is coming from this math package of Python. And then dbl quad is the double integral package. So I am calling this double integral package with all these inputs. All right. If I run this program now, I'll get 0.424413, and the analytical solution is 0.424413 of r. And in this case, of course, we are taking r equals 1 case. So this is r equals 1 case we have computed here. And you see this is the very, very high accuracy of this Gaussian quadrature. So now we can summarize. We have seen that numerically double integrals are equivalent to many single integrals, unlike analytically where double integrals means two integrals. If I want to extend this idea to triple integral, then it's simply straightforward. Also, I have shown you the formulation using trapezoidal rule, but if you want to use Simpson's rule or some other rule, that is also straightforward. Gaussian quadrature is a highly accurate scheme, and that is why it is used in many software. You have already seen it is in SciPy, and SciPy actually takes this package from an old Fortran routine where also this Gaussian quadrature is implemented with very high accuracy. Gaussian quadrature is also used in finite element packages because of its high accuracy. For your exercise, you write a pseudocode or write a computer program to numerically evaluate this integral. You can also try an analytical solution of that. If you do not have the scope of writing a program, just focus on the pseudocode part. If you can run this code which I have just shown, you can take that code and change it like this and try to see that if you are getting the right result. That's all for this lecture. Thank you, and I'll see you in next class.